Okay, so new applications. One of the things that I'd like to talk about today is end behavior. Right? So we're going to be interested in modeling functions. Right? And here we've seen a lot of tools having to do with the shape of a graph, right? So given a function that's just numbers and letters on a page, how can we tell what the graph of that function looks like without having to plot just a bunch of points? And we can find when it's increasing, when it's decreasing, we can find when it's concave up, we can find when it's concave down, we can locate any local extrema. But we might also want to know what's happening all the way to the right on this function. What's happening all the way to the left on this function? Right? So, right, for instance, if a function were to do something like this, the fact that this function is increasing from negative infinity to infinity doesn't mean that it is just always getting bigger, period, and that that's enough for us to tell what's going on, right? Because it is always getting bigger, but there's this upper bound on it. It's never going to get any bigger than, say, if this was something like pi over 2, right? F of x is never going to get any bigger than pi over 2. Even though it's always increasing, that doesn't mean that its shape is like this, and that it will increase without bound. So how can we tell kind of like algebraically what might be happening out here at the extreme values of this function? So one thing that you might do is you might just take really, really big values of x, right? You might come out here and say, oh, well, what about if x is 100? What about if x is 1,000,000? Right? And you can plug those into the function and see what happens. Okay? Do they look like they're approaching a single value? Well, sometimes that's not enough. Right? Sometimes a function might just climb really, really slowly. Say, for instance, the natural log of x. Its graph looks like this. Here's y equals the natural log of x. And you can see that it's increasing, but it's increasing slower and slower. But it does increase without bound. It always gets bigger. It just gets big kind of slowly. In fact, you can name any power of x that's positive, and it gets bigger faster than the natural log of x does. The 100th root of x gets bigger faster than the natural log of x does. The 1,000,000th root of x gets bigger faster than the natural log of x does.
So it gets infinitely flatter without going flat.
It gets, yeah, I guess that's one way to put it, right? It's always, its rate of increase is always decreasing. It's always concave down, right? So it's getting flatter and flatter and flatter, but it never levels off, right? The limit of these derivatives isn't 0. So the slopes aren't, or will always be positive. They're not going to limit to 0. Well, actually, they will limit to 0, just really, really slowly. Sorry, that's a little bit of a lie. They will limit to 0, but the natural log of x will just always be getting bigger and bigger and bigger. These derivatives also get smaller and smaller and smaller. They look more and more like 0. But the function is still getting, while it's getting bigger, it's kind of capped. So the fact that the derivatives limit to 0, the fact that the derivatives are getting smaller and are getting arbitrarily small isn't enough for us to say that there's not some type of end behavior here. This, incidentally, is called a horizontal asymptote. A function has a horizontal asymptote if at either all the way left or all the way right, the behavior of that function looks like a horizontal line, right? F of x has a horizontal asymptote. We'll give it a name. Y equals some number, like a. If the function behavior approaches that of the horizontal line as x is arbitrarily large, or I want to say small, but what I really mean is negative. Small could have a couple of different connotations, right? If you're to go as left on the number line as possible, your absolute value would be really, really big. Right? Negative a million's a pretty big number. So when we say small, do we mean close to 0, or do we mean as far left as possible? So I want to invent some mathematical kind of like language for what this says in words. Right? If you go all the way right on a graph, or if you go all the way on the left, all the way left on a graph, if it can be approximated with a flat line, then we're going to say it has a horizontal asymptote. And that's really nice because I don't have to think of it as this complicated function. Instead, I could just think of it, oh, once x is big enough, it's always going to be pretty close to pi over 2 in this case. This is the symbolism that we're going to use. We say that the limit as x approaches infinity of f of x is a. So this is x getting arbitrarily large. Right? Notice x cannot be infinity. You can't plug infinity in and evaluate what's happening, right? Infinity squared or infinity plus 1, they don't make any sense. Infinity is not a number. It's this kind of concept. So we need these limits to talk about what's happening as we approach that conceptual value, right? If x just keeps getting bigger, what happens to f of x? In a picture, we're thinking this idea. You tell me how close you want to be to A. You say, oh, I want to be within 1/1,000,000th of A. So you kind of create a little bit of a bubble around A. You say, I'm going to either be within 1/1,000,000th above A or 1/1,000,000th below A. Well, if you tell me any number, how close you want to be, I can tell you some value out here, some value of x. So that for all of the x's to the right of that value, I'm that close. This guy in the bubble. This guy in the bubble. The next guy in the bubble. No matter what x value I pick, it's going to be however close you want to be. You want to be within 1 Google, 1/1 with 100 zeros at the end of it? I can come up with an x value so that all of the x values above that correspond to y values that are exactly that close. And it doesn't matter how close you want to be, I can come up with that value. This is the kind of technical definition about how we would describe this limit. The thing I am not going to ask you to do in this class is give me this value. Oh, here's a function. I want to be within 1/1,000,000th of f of x. Find out the value that corresponds to being that close so that we can prove that the limit is what it is. Instead, we'll kind of have shortcuts. Similarly, right, we might have something like the limit as x approaches negative infinity of f of x equals some number. Okay? So in this example, the limit as x approaches negative infinity would equal some value. There would be a value for which that limit exists. That limit's defined, it's y equals b. So if this were b, right, the function is approaching b, the further out we get. Horizontal asymptotes are not lines that the function gets close to but does not touch. Let me repeat that. A horizontal asymptote is not a horizontal line that the function gets close to but does not touch. The function can touch it. That's fine. The whole idea is that the behavior of the function approaches the behavior of a flat line. The function and a flat line basically become indistinguishable from one another eventually by the difference between the two getting next to nothing. Let me show you an example of a time when the function might hit the horizontal asymptote. So here's something that could happen. Notice as x gets increasingly large, the function is getting smaller and smaller and smaller in absolute value. So I might say that the limit as x approaches infinity of this function is 0. Okay? You tell me how close to 0 you want to be. I can tell you some x value so that all of these f of x's are in that window. Okay? All of these y values come back as close as you want. You want to be closer? You want to be here and here? You want to be closer? I can come up with some number that's further out so that all of the y values past that point, they come back in that window. However close you want. That's what it means for the limit to be 0. But you'll notice that this function, it hits 0 all kinds of times, infinitely many times. But all the way out here on the right, you'll notice that the function looks like a flat line. It looks like y equals 0. More and more and more and more. Even though it's kind of wavy, those waves are leveling out. Okay. So here's an easy problem. The limit as x approaches infinity of 1 over x, what do you suppose that is? You're going to take 1 and you're going to divide it by numbers that are getting increasingly large. What happens to that function?
Takes the shape of that graph.
Well, yeah. But what if I didn't know the shape of the graph?
Goes towards 0.
It goes towards 0, right? It's going to be 1 divided by 100, 1 divided by 1,000,000, 1 divided by 10 million. Right? This function approaches 0. In fact, if you had the limit as x approaches any positive number or any non-negative, any non-zero number divided by x raised to a positive number, right? It's going to go to 0. Because you're taking a number and you're dividing it by increasingly large values. So of course you're going to get 0, right? If you take 1 pizza and you divide it by infinitely many of your friends, how much pizza do you wind up eating? None, right? If you have 5 pizzas and you divide it by infinitely many of your friends, you still don't get any pizza. You get 5 times as much, but it's not Not quite enough. So why these examples? We're building up to this type of example. X squared minus 1 divided by 3x squared plus 2x plus 4. Now the numerator of this function is getting really, really, really big, right? I'm taking a number that's getting infinitely large, and then I'm squaring it and subtracting 1. So I have Bill Gates' net worth, I squared it, and then I subtracted 1. It had $1 to give, right? That's still a lot of whatever. And down here, I took 3x squared, I added twice that number, and then I added 4. This is also getting really, really, really big. This looks like infinity over infinity. The top is getting infinitely big, and the bottom is getting infinitely big. This is another indeterminate form. Just like 0 over 0. Remember, with 0 over 0, the top 0 is wanting to make the function look like nothing. But the bottom 0, as you're approaching 0, you're dividing by smaller and smaller fractions, and they want that fraction to be big. So there's a tug of war happening between the two parts of this limit. The top wants to make it look like 0, and the bottom wants to make it look like infinitely large. Something similar is happening here. The top infinity, right? The numerator wants to make this fraction really, really big, but the denominator wants to make this fraction really, really small. So there's a tug of war. I don't know who will win out. So here's where I'm going to remember this type of guy. What if I came in here and I said to myself, Jonathan, I says, I don't like the fact that these are polynomials. I would much rather have little fractions like this, because I know what happens with little fractions like this. So I'm going to come through here, and I'm going to divide all of these values by some power of x. Anybody have a favorite power of x that they would like to divide this function by? I like x squared. Why might I like x squared? It's in the top, but I mean, I'm not worried about the top just yet. I'm looking at the bottom. It is the highest power. So what good does that do when I move this in?
Well, that's what's going to affect the graph most.
True, right? These leading coefficients, these leading terms are going to have the most effect on the function as a whole for polynomials. Right? So I'd like to eliminate this biggest power if I could. Notice 3x squared divided by x squared is just going to be 3. So I've gotten rid of this guy. But what's happening with these other ones? I have 2x divided by x squared. So one of those x's is going to cancel. So I'll just have 2 over x. And I'll have 4 divided by x squared. So it looks like this. It looks like 3 plus 2 over x plus 4 over x squared. Why do I like that better than what I had? If at all. Maybe I don't like it better. I like it better.
Aren't those trailing exponents irrelevant though?
Effectively, but this is going to give us a reason why they're irrelevant for in behavior. What happens to 2 over x if x gets infinitely large? It'll approach 0, right? What about 4 over x squared? What happens to 4 over x squared if x gets infinitely large? It also approaches 0. What happens to 3 if x gets infinitely large? It stays 3. This limit, the limit of 3 plus 2 over x plus 4 over x squared, is a limit that's really easy for me to evaluate. Its limit is 3. This bottom, now instead of getting infinitely big, now it looks like 3. Because this guy goes to 0. This guy goes to 0. And 3 just stays 3. So what I've been able to do is kind of eliminate the behavior of the denominator as a factor. Well, I left that 3 around. Why didn't I just pick a higher value of x? Why didn't I choose to divide everything by x cubed or x to the 5th or x to the 100th? I could have just wiped out everything. How? That'd be all zeros. I wouldn't know what to do, right? If I pick too high of a value of x, all of them will zero out. Okay? This is the baby bear issue. Right? I'm going to pick the value that's just right. Because if I pick one that's too high, all of the terms will zero out, and I'll be dividing by 0, and I'm in trouble. And if I pick one too low, not enough will zero out, and it'll still be getting infinitely large. But by choosing the highest power of x, I'm able to get rid of all of the things that are not the highest power, and I just eliminate the highest power, leaving its coefficient behind. The reason that I don't want to zero everything out is why I start with the denominator. I don't care if I zero out everything in the numerator. If the numerator of a fraction is 0, well, it's 0. But if you zero out all of the denominator, then you're in trouble. So that's why I started down here. And whatever I do to the bottom, I've got to do to the top. So I'm really just multiplying by 1, right? I'm multiplying and dividing by the same value. So I'm leaving this expression unchanged. So now the numerator looks like x squared divided by x squared, which is 1, minus 1 divided by x squared. Right? 1 divided by x squared. And what happens to 1 over x squared as x gets infinitely large? It goes to 0. No big surprise. So what is the limit of this function as x goes to infinity? 1/3. Easy enough, right? This is the general idea, and it works for negative infinity as well, right? Because if I took 2 divided by negative infinity, it's going to approach 0 also. It's just going to be a negative number instead of a positive number, but that negative number is getting infinitely small. And if I take negative infinity and I square it, I'm still talking about a huge number that I'm dividing into 4. So this is also going to go to 0. So negative infinity limits work exactly the same way. Rational functions, they look like some polynomial divided by another polynomial. X squared plus 2x plus 3 divided by 3x squared minus 2x minus 1. Or x plus 2 divided by x to the 5th. Or x cubed minus 1 divided by x plus 1. A polynomial divided by another polynomial. That's what we mean by a rational function. Whenever you have an infinite limit of a rational function, you can employ that previous technique, right? You can identify largest power in denominator, right? divide each term in numerator and denominator by that power, and then evaluate the limit. Right? Boom, boom, boom. They all get approached exactly the same way. If we had time, we would find that as we saw more and more of these problems, that there's a pattern to the way that these evaluate. This first function, if I divide everything through by x squared, you'll notice it's going to eliminate this 1, it's going to eliminate this 2x, and it's only going to leave the 3 in front of this x squared. And in the numerator, it'll eliminate the 3, because it'll be 3 divided by x squared. This 2x, that x isn't enough to cancel out all the x's in the bottom. And this x squared cancels all of the x's out evenly. So all I'm going to be left with is 1/3. Whereas something like this guy, x plus 2 over x to the 5th, if I divide everything through by x to the 5th, right, it's going to eliminate this power, the highest power in the denominator. It'll just be leaving me with the 1, this leading coefficient. But in the numerator, everything is smaller than 5. So by dividing by x to the 5th, it's going to come through and wipe out everything on top. So this is going to look like 0 divided by whatever this leading coefficient is. So this is going to go to 0. And here, this x, the highest power here, it's not big enough to wipe out everything on top. So I'm still going to be left with an x squared. So just the relationship between the leading terms will be enough to tell me about in behavior. If the leading terms are the same power, right, then that infinite limit is the ratio of leading coefficients. Right. Yeah.
So that third example, you have the x cubed minus 1 over x plus 1, that's approaching infinity.
Yeah, that'll get infinitely large. Because it's going to look like x squared does, and if x goes to infinity, x squared looks like infinity. If the denominator is bigger, then the limit is 0. And if the numerator is bigger than the denominator, then the limit is either going to go to positive infinity or negative infinity, one of the two. Both are just fancy ways of saying does not exist. But it's a little bit more specific. Because you can not exist and kind of alternate, right? You could start off and then kind of be getting bigger and smaller. But by saying that the limit goes to infinity, you're saying that it increases without bound. By saying that it goes to negative infinity, you're saying that it decreases without bound. So it's kind of a more specific way of telling you something about the behavior. But here's a way that we can kind of cheat on these infinite limits. Right? I can just spot, oh, the biggest power is x squared, the biggest power is x squared. If I have an infinite limit, then 1/3. Okay? Oh, the biggest power is 1, the biggest power is 5. If I have an infinite limit, this limit is 0. If the limit is something else, it doesn't work. Right? The limit of this function as x approaches 1 is 1 plus 2 is 3 divided by 1. Right? We could just plug and chug the way that we used to. This method only works for infinite limits. This is the power of infinity. That if you divide a real number by an infinitely large value, it will approach 0. This is one of the ways that infinity and 0 are tied together, kind of. Any questions about this? So this is a way that we might identify horizontal asymptotes by taking limits as x approaches infinity or negative infinity.